good, and also reasonably good ionic conductivity. And also we don't have any problem with what they call as a contact problem. Just you put few drops of electrolyte, so your problem is solved. It's the same thing if you use with solid electrolyte. Contact is a major issue. So another disadvantage of this liquid electrolyte is the leakage problem and sealing. And sometimes we know that during the charge discharge cycle, there is a flammable issues, like safety is a big issue with this battery. That's why there is huge interest on the liquid electrolyte. People are going to replace with the liquid electrolyte by either polymer or solid electrolyte. So polymer electrolyte, I told you that this early concept has been developed by Michel Armand, by French researcher. And also he was with Montreal when he's closely with some of the lot of technology has been commercialized with the Quebec. So solid electrolytes, we broadly classified, I told you the crystalline and glassy materials, mainly oxides and sulfides. So here, the main issue is that if you want to be any solid electrolyte, so here the conductivity like ion mobility. So we need a vacant site. So and also with the simple formula, people can calculate the ionic conductivity by knowing the thickness, resistance, and then the area of the electrode. So it's very important to consider what type of the solid electrolyte. So we have to look for the high conductivity in the order of 10 to the minus 3 to minus 4 Siemens per centimeter room temperature, and we want to be low electronic conductivities and good electrochemical potential window, in the sense that you have to go to 5 volts or 6 volts is really good, and good chemical stability with wide temperature is very important. Sometimes we are going to heat the electrodes, both cathode and anode. Stability is very important, play an important role. And also what they call as transparency number nearly close to 1, you have to good, so mostly we will not get. So it is very important. Sometimes cathode anode materials we are using, so while sintering is very important to now to make a good contact between the cathode and anode and electrolyte layer. So thermal expansion coefficient has to match with both cathode and electrolyte system. So it's very important. There is no, as I told, the liquid electrolyte, good chemical stability, no crystal structural transformation during the heating or during the electrochemical cycling. So, and also at the end, we have to look for the low toxic and cost effective. I think mostly nowadays people are concentrating to solve all above points. I think later people, they work for the toxicity and especially cost. Cost anyways, presently cost is slightly higher because people prepare in the small scale. If you scale up, automatically cost will going to reduce. So these are various type of nano materials related to the energy storage and conversion. So what I am going to tell you here is that since you people are chemists, you can try to prepare the material during the electrochemistry or based on the collaboration. Some, for example, some people have expertise in the photocatalysis, or some people have expertise in sensors, or some people are expert in supercapacitor. So this way, as a university researcher, sometimes I know that due to time funding limitation, all the people cannot buy all the instrument. So it is nice to collaborate. I think some people are able to prepare the materials. At least it is a way to work as especially young researcher. As a faculty, I don't think not much time. At the end, as a young researcher, you to try to look for the collaborate within your group or the next to your university. That will be easier to what they call some material. For example, TiO2 is well-known materials. I think people can use for various applications, starting from not only in battery material, also solar cell, photocatalysis, etc., and also many other applications people can use. So what I'm telling that since is, so with the materials, at least we can do a lot of applications. So at the end, overall summary here is that I think collaboration will play an important role in order to make at least good output, what you are trying to going to prepare the material. Although we claim that this material one material cannot be utilized for all applications, depending on the applications, people have to prepare accordingly and with a proper substrate. These are the various materials we are going to prepare. So it is very important. Chemistry will play an important role. So here I'm to touch up with a few material senses related to what is useful for you people. So the various material senses we've been adopted for the last 10 years. starting from solid state synthesis, molten salt, carbo or graphenothermal, etc., etc. So, for example, since a very physicist, sometimes some few cases we are going to use thin films. So, advantage of this technique is sometimes for nitrides. So we notice that the RF sputtering is really good. For example, you want to make a thin film batteries as a physicist, or if you make a thin films with the same thin film, people want to see with what they call electrochromics or a color change. People can use RF sputtering. And so, see here, I'm going to tell just one message. Some people, I know that sometimes physics department, they're very much interested only in physics related, for example, RF sputtering. Since they have facilities, they can code the sample, for example, tin oxides or indium tin oxides or whatever the tungsten oxide. They can they can code the sample on a ITO. So you as a chemistry people, so you can do electrochemistry at various voltages. You can study the electrochromics. So the see here you can you can links both the physics, physicist and chemistry. Although some materials may be useful for the battery applications. So these are various type of the materials characterizations we are going to use. So starting from the uh, X-ray diffraction technique is a very useful technique. So it's very important as a battery chemist. So we need to know the impurities as well as lattice parameter. Sometimes we use layered compounds. Cation mixing is very important to look for this. XRD is a basic tool. And sometimes we can do more fancy technique, for example, neutron, X-ray diffraction. I think without this one, since the university, all people cannot access, still the main as a starting point, X-ray diffraction will be useful. For example, thin films is a little bit more complex because since thin films are amorphous or sometimes may not be really 100%. For chemical compositions, it's nice to do with the Rutherford backscattering spectroscopy. If it is a light elements like lithium, sodium, we need a nuclear reactions, and sometimes homogeneity of thin films by OSHA and XPS, X-ray photoelectron spectroscopy to know the oxidation state. Again, it's very difficult to conclude based on the XPS with exact composition. So we need a complementary tools to know the exact composition obtained by XPS by other technique. And these are other techniques I think you people are going to use, well known like IR, Raman, and density, surface area, etc. As a electrochemistry per battery point, we need a galvanostatic cycling and cyclic voltammetry, or we need impedance analyzer. Nowadays, with a single instrument, we can get all three in a one unit. Uh, so and also SCM, uh, TM. So what my experience is that since you're doing with a electrochemist or battery research, since you know the basic first thing is XRD, followed by electrochemistry. Later you can do, if you're really interested, really interesting, you can do TM. Sometimes I know that TM is not so easy to access all the university people. So at the end, if you have simple XRD based on the electrochemistry, and since the results are really good, you can do further studies, like example, TEM, SEM, and further studies. So one slide I'm going to talk about why we're fascinated about the molten salt method. Since I work with school kids from junior college, so these techniques I noticed very simple, and also not many people have been explored in these techniques. I thought, why don't we look for this technique? So also we call as a MSM, um, molten salt method is one of the versatile method to obtain the, and also highly crystalline materials starting from the energy storage as well as the catalysis materials. Usually when compared to solid state reactions, reactivity will be very good in case of molten medium. So it is like chocolates. For example, chocolate, it will melt at a particular temperature, it becomes a liquid. As a consequence, uh, so for example, excess of molten salt, 6 to 10 moles of molten salt, react with the respective metal salts with 1 molar, what is the composition you want you to design here, and put it in alumina crucible. Is very important. Don't put any glass beaker because it will react. So heat at various temperature, whichever the temperature you want. Actually, based on our studies, we've been explored from 140 to 800 degree temperature. And time also you can start from 30 to 12 hours depending on the oxides. So it's very important at the end we have to wash with the deionized water or distilled water to remove the excess salt, and finally filter the sample. So within one night, for example, one night you can keep the sample in the furnace. Next day you can come wash the sample. So almost like some 10 to 5 to 10 grams you can prepare. That is enough for your all the further characterization. So at the end, you are not spending much time on the material synthesis. Later, use this material for the various characterization techniques. So what I am going to tell in summary, with the molten salt method, you can play with depending on the salt, reaction conditions and time. You can you can play with the morphology and crystal structure, etc. So early work we started in the 203 or 20, or at the time our interest was only layer type cathode materials. So here, so lithium cobalt oxide for molten salt seems to be promising. If we do with more manganese, seems to be not really good if you use same nitrate salt. For example, LiMn2O4, you can prepare, we cannot prepare using lithium nitrate, lithium chloride. Why? Because it will form Li2MnO3. This is like it's impure phase. It may not be really good for the battery. So we have to do the chloride salt seems to be better. So what I in summary here is that depending on oxide, depending on the oxidation state, try to select a proper molten salt. And also we've been explored titanium dioxide with the various different type of molten salts. In summary, we are able to prepare the sample starting from 140, nearly 140 degree, we get amorphous TiO2 and nanocrystalline by 175. And also 280 degree also we can prepare nanocrystalline material. At the end, in terms of the electrochemistry, high surface area, 280 degrees seems to be really, we get nearly 200 meters square per gram. Without, we are not using any surfactants. Without that one, we'll get nearly 200 meters square surface area we're able to prepare the sample. Although we try to look for some of the mainly presently some of the study, although we, since these are high surface area material, in addition to batteries, sometimes with the collaboration, we've been look some of the solar cell properties also. So, so these are the other oxides you've been looked. So since it is, you can play with the various spinels, starting from cobalt oxide. So if you use same lithium nitrate, lithium chloride salt with nickel and cobalt, seems to be, we're not able to prepare the samples. The pure phase we can obtain by using the zinc, cobalt and copper. And recently something cobalt, iron oxide. So it's very important. If you use cobalt and iron combination, we have to go to slightly high temperature only, we're able to get prepare the samples. So for example, tin oxide also we can prepare at 280 degree. And similarly with various other oxides. After doing all oxides, since our interest was electrolytes, we try to prepare the concept by using garnet-based electrolytes. In fact, this system is very popular. So we noticed that although this is the first time we've been looked in the system, so it seems to be due to proton exchange in the during washing, this molten salt method may not be really good. So we are not able to get good conductivity. So what I'm going to, the overall summary is that I don't claim that this molten salt method is universal for the all type of the material. So depending on applications or depending on the oxides, we have to use a proper material synthesis. So we have been, another thing is the carbo. It's early work we started with the carbon. If you use a carbon, we call it carbothermal reduction method. Grapheno thermal reduction method is called grapheno. If you use a reduced graphene oxide, we can call it grapheno thermal. Advantage of this technique is that, so we're able to, at a consequence, we can do graphene coating as well as some exfoliations, conductivity will improve. So, and also we've been explored various type of graphite and what they call as RGO and graphene samples. So overall summary, the application point of view, it may not, although we'll get slightly higher capacity, it may not be really interesting with the graphene alone. So that's why. So in summary, if you want to make any graphene or carbothermal reduction, the minimum temperature you have to look around nearly 650 degree in argon. It is very important. You have to put the sample in a tube furnace in the argon. So we are able to get a respective, so just I'll note down time, okay. So we are able to get a respective oxides. So, and also we can prepare the samples with the various, for example, MOO2. So, beauty of this technique is that we're able to get reasonably good, good materials with a graphene coating. So overall summary is in terms of commercial graphite, you can see the top left side. And this is a graphene. I think people have climbed this one although we claim some 1000 milliamps, in reality for the application this material may not be really useful. So we have to look for the materials, so we get a lower capacity. What are 1000 milliamps at lower potential is very important. That's why although people have claimed the graphene can be used for all, it may not, since what people are using for batteries, they use a graphene as a current collector. They can coat one layer and the either cathodes or anodes, so that one they can use it for the, so graphene acts as a nice current collector for the battery materials. So another thing is a co-precipitation method. So this is a good thing. So since with a small beaker and a burette, you can do precipitation methods. You can prepare the simple oxides, for example, layer type compounds, for example, lithium one third O2. So here, so not avoid the nice mixing. This technique is more popular. So nowadays, industry think they're scaling up the synthesis in terms of tons of the quantity by using the batch reactors. Here, the chemical engineers will play an important role designing the reactors for the color co-precipitators. So what I'm going to tell you that although the batteries, the laboratory scales, we can do simple burette and with a beaker, you can do the synthesis. And if you go for industry, I think people want to, they can prepare the standardize the sample at the large scale preparation. Again, you can play with the depending on the base and then concentration of pH and alkali solution. You can you can do, and also sometimes people can do different types of surfactant also. Another way is a ball milling approach. So suppose you want to take any nanomaterial you want to prepare, you can mix with respective metal oxides with a ball. So with depending on time and ball milling speed, you can prepare the nanomaterials. Also sometimes here what I'm going to summarize is that the battery chemist, so we need a better matrix element in order to get a good battery performance. So another way is the combustion method. Here, these are the slides I'm telling because although this technique is known, it's not really new one. Since with a small beaker with a hot plate in your lab, you can prepare the material, do the electrochemistry also. Since electrochemistry, you may need very small sample, so it's nice to prepare this techniques. Sometimes depending on the oxides, we can get porous materials, and still you can play with various depending on the fuel and oxidizer and temperature. We can prepare the materials. So another is electrospinning techniques. I think this technique is more like other engineering people. It's not my own interest. So it's my collaborator from Ram Ramakrishna. So idea is that since we work with mechanical engineering, so as the engineers, so they're very fond of this preparing the fancy structure. As an electrochemist, I'm going to look for this electrochemical properties. In summary, so this material may be really good. Although so if you decompose the sample, any electrospinning materials near decomposition temperature polymer, it may be good. If you exceed that temperature, you'll get almost like a highly crystalline material at the end. We can get the, so as you can see, the particle size reduction as well as surface area is going to reduce. So particle size increase as a consequence of high temperature, and surface area is going to decrease. So I'm going to tell you in summary, although I don't claim that the electrospinning is a large scale preparation may not be, since anyway nowadays recently depending on applications, people are looking for the large scale preparation techniques. So overall summary is that, so in order to prepare a small milligrams or 1 gram sample, you have to spend nearly 15 days. With a simple molten salt approach, we can do 1 day or about 2 days maximum. We can prepare the almost like 10 grams of the sample. So still depending on the application, for example, people want to study the electrocatalysis. They want some nanomaterials from metal oxide and any metals they want to do. They can do electrospraying as well as electrospinning. That's why because depending on the design, people can prepare this material. So another approach is hydrothermal and solvothermal approach. If you use water, we call it hydro. If you use a solvent, we can use a solvothermal approach. So, and also here what I'm doing till that is depending on the application. For example, if you want to use lithium air or supercapacitor, they use a nickel mesh as a current collector. So they can coat the sample on the material, and here people they can use the respective metal oxides. So nitridation we've been looked because nitrogen we can react with the 3 lithium compared to the oxygen. So next slide I'm going to tell about what is the drawbacks. Although this academic wise is really good, in terms of the voltage potential we are not able to get. Since I have almost like 10 minutes, another 10 minutes time, I'm going to so touch up some of the few examples related to my work. So this also we look some of the fluorine with the PVDF binder. Also, we can try to prepare the samples by using the fluoride-based materials. So this is one slide tell about the battery fabrications. You take any either cathode, anode, 78 or 88% of the active material, followed by carbon and mix with the carbon binder. And finally, we can coat either anode is a copper foil. For the cathode, we have to use the cathode, we use aluminum foil. Finally, roll it and make into coin cells like this way. So this is a fabrication of the cells. As you know, the real electrochemistry, people are going to use a 3-electrode system. Since it's a 2-electrode system, we are going to use. So here, the beauty of this is why the reason is for applications always we depress both cathodes and anode, and they usually contain cathode, electrolyte, and anode. So finally, these are the voltage limit we are going to use. I told you that for your battery, laptop contains cylindrical cells, and coin cells is the cells we are going to use for the laboratory scale. And depending on industry, people are using the different design. Here you have to remember, if you go for large scale, safety is a big issue. We need a proper electronic design, what they call it, the temperature, everything. People have to look for this thing. These are various characterization techniques is available, starting from the battery tester here, last left side, and glove box. So because since we lithium were working, and impedance analyzer, and few other techniques are available. So I told you how to calculate the capacity. Capacity is nothing but how much time is taken from either charge to discharge, charge, followed by uh, how much time multiplied by current divided by weight of the materials. So this is called capacity. And I already told you about how to calculate theoretical capacity. So good thing about we need a good lithium diffusion coefficient by GATT techniques we are going to do. Cyclic voltammetry is a very important technique to know the redox couple as well as kinetics, and also is a well-known technique you people are also going to use in the solution electrochemistry. I think similar concept people can adopt. So it's very important. Peak current is directly proportional to the scan rate, and then what they call as the area, etc., etc., and also thickness of the electrodes. Higher the thickness, higher the peak current. So as a layman's explanations, we need a reversal peaks is really good for the batteries, and also try to understand the structural transformation. So impedance spectroscopy is a very well-known technique. So we have to use this technique to understand the what is happening with respect to the charge transfer, surface film, and the bulk resistance. So here beauty of this technique is very useful to understand the, since you people are not more expert, if people are interested, I am happy to discuss more detail on the system. As a layman explanation, if it is battery during charge discharge or one single semicircle, after charge discharge, we get a few different semicircle. Although we can do some complex modeling, so we can do different type of different circuits. Again, although interpretation is very complex, so that's why people have to use a simple model, make sure that what you're going to do, accordingly try to discuss with a proper model. So this is a commercial cell, people are going to how these color beauty, so depending on cable, we'll get some inductive behavior. So these are various type of cathode materials, starting from we call it cathode means 3 to 5 volts, anode 3 to 0 volts. So as we know, the presently safety is a big issue of the lithium batteries. That's why I told sometimes you can see batteries going to bulge or sometimes safety issue. So I'm going to tell one slide how what is the probable reason. So we are able to study the in situ technique. So we put the same batteries in the XRD during the real time. Sorry, another. So real-time XRD system. So from this technique is very useful to understand what is happening during the charge and discharge. So these are the in situ patterns. These are all the sample collected by using nearly 2 days. What will happen during charge, the lithium, what they call D value is shifting to lower angle. And this is mainly due to the what they call as volume expansion. So changes in the lattice parameters. That's why due to safety limit, they will stop nearly 4.2 volt limit. And reason for this one, so due to the simple explanation, since you electrochemistry, I can tell that oxidation reduction during this some structural transformation is going to happen. So anyway, really complex since, so as a solid state chemistry, so what will happen during the charge discharge, there we can see the changes in the lattice parameters. Nowadays, recently, people are using very fancy technique like solid state NMR. So real time battery, what is going to happen with respect to the lithium and electrolyte surface, etc., etc. So regarding the cobalt oxide, I think these are the advantage, disadvantage also. So that's why people have been look for the various type of the cathodes and cathode materials. The mainly now presently commercial thing called NMC, NCM is one third means like this composition. This early work with our group as well as Japdan and also Wazuku in 203. I think now this sample is commercialized. Lithium iron phosphate is John Goodenough and also the valence technology and LIM into by other researchers. So in the one slide, I'm going to tell that really good batteries means we have to get higher voltage. That's why we look for the lithium iridium fluorophosphate. And this material seems to be reasonably stable up to 7 months, 6 months. We've been cycle almost reasonably good stable and also good thermal stability when compared to the lithium cobalt oxide. Also, this is some of the collaboration with Professor Vittal from chemistry department. We try to prepare the metal organic new framework materials. Advantage is vanadium complex system seems to be good. Nearly we are able to get a 4 volts. So beauty of this material is, although we'll get slightly 4 volts, the capacity is almost nearly 110. So although we climb that high impact factor like journal for real applications may not be, although this concept has been early with the first time we've been reported, still there is a scope for these materials, try to get high capacity nearly 150 or 170 really useful for real application. In terms of potentials compared to lithium iron phosphate, nearly 4.5 volts is good. That way, positive results. So one slide I'm going to talk about why the sodium battery. Sodium battery compared to sodium and lithium, for example, lithium iridium fluorophosphate will get 4.2 volts. If you do same thing with the sodium system, we'll get 3.5 volts. That's why if you go for sodium, the potential will be low. Automatically, we'll get lower energy density, and also handling the sodium may not be really good. Still, cost is lower. That's why people are looking for the sodium as alternative materials and with stationary applications. So regarding anodes are concerned, these various type of the graphites people have been used. Here the safety is a big issue due to lithium dendrites. I think in order to avoid this one, nanotechnology, people are going to reduce some by using the nano size materials, followed by matrix element concept have been done. So I'm going to finish within another 2 to 3 minutes. So so these various type of the anode materials we been looked in the laboratory. I think early with Japanese researcher by tin oxide, followed by various combination of wind and overall summaries in terms of electrochemistry may not be irrespective of metal oxide. We are able to get nearly 0.25 is what they call a reduction, 0.5 volts is oxidation. So summary is that so matrix element play an important role. As academic research, it's nice to look for some new materials with low capacity, etc., low capacity fading, etc., etc. So this is the one slide I'm going to tell about. If you take with nano size material seems to be better. That's why we are able to cycle well. And also at the end, as impedance spectroscopy, we were able to get nearly smaller resistance. So here, lot of anode materials been looking all over the world in literature. So here, this as a academic researcher, extensive research going on this material. Again, for application may not be really challenging because unless if you reduce this discharge potential to the lower voltage and charge potential further lower voltage, generally really application. Although we can climb some capacity, so we don't have any proper matching cathode and electrolytes. So there is a little bit challenge. Still, there is a huge research is going on from this one. Some of the early contribution from the France, followed by few other spinel from our group. So nitrates, I told you that although we get slightly higher capacity, the reality is the potential is not changed with respect to the oxides. That's why, so anyway, already academically, overall summary is that if you take nano size material, nano flake, start from nano to bulk, and vanadium nitrate, chromium nitrates, and titanium nitrate may not be really interesting for the battery applications. So various type of intercalation reactions have been done in the literature. Among them, TiO2 is well known. The overall summary in terms of electrochemistry, LTO nearly 1.5 volts we are able to get, so really good. So although sometimes we may get higher capacity, the potential reduction is needed for the real applications. So this is one example. If you go from nano size to micron size, the capacity will reduce. So the reason is that, as you can see, the electrochemistry will play an important role, starting from the broad lines and sharp lines. The sharp line also clearly indicates a good intercalation behavior. So these XRD patterns. So the summary, starting if you prepare the sample with low temperature, surface area is really good. And if you heat the sample simply at high temperature, surface area is going to decreasing. High temperature seems to be brittle phase, so it may not be really good for the applications. So I think I'm going to touch up on the another slide. Here, solid electrolyte will play an important role if you want to work with redox flow batteries or aqueous lithium air batteries. So usually electrolyte is a system, so it will be more stable with water and then non-aqueous electrolyte. So these are various electrolyte beams based on the sulfide system. So many sulfides that people are going to use for the present day lithium battery solid electrolyte system. The main issue here is that sulfur handling is not so stability. Anyway, there is a lot of challenges is going on this type of the material. Although material is known in terms of technology is not really well established. That's why there is huge interest in the worldwide researchers. Regarding oxides are really good. Only problem is if you sinter the sample with the cathode anode, there is a reactivity with the either electrolyte and cathode material. That's why there is a problem with what they call as electrode electrolyte interface, especially doing that what they call doing the sintering, the mechanisms to be figured out. And these various solid state batteries available in the literature. So sometimes in the physics department, if some physicists are there, you can make a large sputtering unit. You can make a layers of cathode, anode electrolyte and anode. Although you need an expensive glow box as well as a sputtering unit. So that's a little bit drawback in this technique. Again, really challenging. So especially supercapacitor is good for the university researcher with the same electrochemical setup, simple with aqueous electrolyte you can do, we can play with a lot of supercapacitors. Overall summary, I think that since the same material people can work with the battery as a supercapacitor, you can do some studies. And also some materials may be useful for the electrocatalysis. I think sometimes the same material, what I'm telling that since depending on expertise, depending on facilities, with the same electrochemical instrument, depending on the availability of the student, people can do the electrocatalysis, etc. Anyway, although at the end for the applications, since although we climb the too much studies on the system, so it's very difficult to understand which material, no trend we've been seen with respect to the various metal oxides. So this is my conclusion. So since already I'm almost I'm 2 minutes extra, so I'm going to conclude. I'm taking almost taking 2 minutes extra time. So I'm going to conclude my talk. So we've been done in for the last 10 to 15 years. We've been extensive research has been done on the especially material synthesis. Although we don't claim that really experts, still a lot of challenges are there at the end. So all the materials may not be really not using for really commercial application because a lot of challenges are there. So at the end, overall summary is that for the applications, people are looking for the low cost materials and safer materials. Still, nanotechnology will play an important role, especially if you want to with high current rate, nano material seems to be better. And at the end, one word is the battery is a multidisciplinary science and engineering. I think cooperation is needed between scientist and engineer. So it's very important for the large scale production of the batteries, or you want to integrate these battery system. I think I'm going not going to touch more on this big conclusion on solid electrolyte. Finally, I would like to thank you. And due to time limitation, I'm not able to tell more large scale what they call as the hydroquebec. So you can go to YouTube. Some of the few links are available in the online, so people can visit some of the things. And also, thank you very much. Okay, thank you. And also some of the small announcement about these internal issues. Thank you.
Thank you, sir. Thank you very much. And you explained on the lithium batteries and energies and water, healthcare and nanomaterials, energy storage and conversions and applications are very useful, sir. And also your talk on advanced functional materials, properties of the cathode and anodes are wonderful and effective manner systematically delivered. Thank you. Thank you very much, sir. Once again.
Okay, thank you.
To Prashanthi ma'am.
Thank you, sir, for giving a nice lecture overall on the importance of batteries. Thank you very much, sir. Can I expect 1 or 2 questions from audience?
Yeah, no problem. Okay, or if you have,
For 1-2 minutes, please.
yeah, no problem. We can take some more time also. I'm happy to answer.
I think other speaker will be ready for that.
Yeah, you can send email also if later if people want also.
Yes, sir. Yes, sir. Yes, sir.
So I have to unmute or okay, I think it's okay.
Yes, sir. Thank you very much, sir. Once again, on behalf of Department of Chemistry and Pharmaceutical Sciences, Mahatma Gandhi University, sir. Thank you very much, sir.
Okay, thank you. So anyway, thank you. Maybe I'll be in the line or again to relink the next talk. For the next talk, I have to exit and then I have to.
Sir.
Okay.
Next speaker will be Ramanujacharya, sir. If you, sir, can you wait for a few more minutes, sir?
No problem. Okay.
Sir.
So yeah, thank you.
Thank you, sir. Sir. Now I request Professor Ramanujacharya, sir. Sir, may I know, sir? Sir is available. Hello, Chari, sir.
Yes, I'm here. Can you hear
me? Yes, sir. Good evening, sir. Good evening, sir. Please welcome, sir. Once again, I welcome you on behalf of Department of Chemistry and Pharmaceutical Sciences, Mahatma Gandhi University, sir. Now I request Jay Shankarachari, sir, to introduce today's guest of honor and valuable speaker. Over to Shankara. Shankara. Hello, Shankar, sir?
Madam.
Yeah, please, sir. You are audible.
Okay, madam. Thank you. Madam, good evening, everyone. Myself, I am Shankarachari, the Department of Chemistry and Pharmaceutical Sciences, the Mahatma Gandhi University, Nalgonda.
Please increase your volume, sir.
Okay, madam. Ma'am?
Yes. Yeah, you can.
Okay, madam. Thank you. I am Mr. Shankarachari, Department of Chemistry and Pharmaceutical Sciences, Mahatma Gandhi University, Nalgonda. It's a great pleasure to introduce Professor K.V. Ramanujachari, sir. Yeah. Ma'am, okay?
Yes, you can.
Okay. Sir was completed his BSc chemistry from Andhra University, Vizag, with the college topper, and did his MSc chemistry from Andhra University 1976 to 1978 with gold medal. And Sir was completed his PhD, the great IIT Madras, in the year of 1978 to 1982. And after that, he was joined as a research associate in the Department of Chemistry. After that, he was promoted to getting the job, the assistant professor in the Department of Chemistry and Physics, Rutgers University, New Jersey, from 1988 to 1993. And after that, Sir was as associate professor in the Department of Chemistry and Physics at the Rowan University in the Glassboro, New Jersey, from 1994 to 96. After that, Sir was
Hello.
till date, yeah, ma'am.
Please proceed, Shankar.
Okay. And after that, Sir, research areas is oxide chemistry of transient metals and mixed metal chalcogenates, electrical and magnetic properties of materials, ionically conducting polymers and oxides, sensors for humidity and pH, and after that, heterogeneous catalysis. And also, Sir is a membership in the American Chemical Society with affiliation to the South Jersey ACS chapter, and also the Materials Research Society of Singapore. Sir also published more than 220 publications in the various international journals, and Sir also guided the more than various number of PhDs. And Sir is also funding agency from the co-authored as a comprehensive solution manual for the book Inorganic Chemistry by Shrivert and Atkins of Oxford University Press. It's a great book. Also, I've also read it. And courses started in the Rowan include, that is a chemistry, advanced college chemistry 2, and physical chemistry is the preparation for college chemistry as well as interdisciplinary material science across the curricular course taught by the facilities from the chemistry, physics, and engineering. And also, SAR also designed the new courses and the advanced inorganic chemistry laboratory books as well as introduced experiments that give the students hands-on experience with the synthesis of important inorganic complexes. This is also very useful to us. And also, SAR imported the descriptive nature of the subject matter that is not covered in the other courses, the BSc chemistry curriculum. And also the preparation for college chemistry new materials course designed for the improving the retention of the students in the freshman chemistry courses. And also SAR has a lot of citations, almost it is a very big number, almost 5,500 citations, as well as H index with 40 and item index with 121. It is a very happy to introduce to our university, as well as I want to listen and your topic. Very thank you, sir. Welcome to seminar, sir. Thank you, ma'am.
Thank you, Shankar, for giving very good introduction about today's guest of honor and valuable speaker. Once again, I welcome Sir Ramanjachari sir to our department. Please, sir.
Thank you, Professor Chari. I think you have been very generous in introducing me, and appreciate your time taking introducing me. I'm also happy to see Dr. Prashanthi Madam, who took all the pains in organizing this conference, which by no means is a simple task, but she has done a great job. I was listening to the talks yesterday, Professor Meriti and Subhash, so that was a wonderful talk. And my good friend M.V. Reddy, I'm happy to see him. Knew him for many years from Singapore days, and have interacted with him quite extensively. And he was also kind enough to do one of our nitrofluoride oxides of the titanium and looking for the lithium-ion activities. So it is always a great pleasure to see him. And I think he has given a marvelous lecture in terms of introducing the whole world of lithium-ion batteries. I don't think there is anything that he did not touch there in that talk. That was beautifully done. And thank you, Dr. Reddy, for enlightening the students of the Mahatma Gandhi University. So today, my talk is going to be on the ubiquitous nature of nanotechnologies. So what I'm going to do is, if you allow me, I will try to share my screen.
You can, sir. You can, sir.
I can? Okay.
Yes, sir.
All right. Let me see if you can see it. Can you see the slides?
Yes, sir. Visible.
Okay. Wonderful. Can you see the whole slide, or you see the side panel too?
Whole slide, sir.
Whole slide. Okay, wonderful.
Yes.
All right. It's so nice that Dr. Reddy, who spoke before me, did a great job, gave me a good lead into the importance of nanomaterials, whether it is in the battery industry or whether it is for catalysis, whether it is in the biochemistry. Nano is becoming extremely important. I'm sure most of you must have seen this, or must have heard about the name nano. Nano means small, 10 to the negative 9th of a meter. While the sciences may not be really new, because a lot of times we knew that materials, when you reduce the size, have important functional properties. Not only in the laboratory, but even in the kitchen too, right? When you are using turmeric powder, right? You don't use a big turmeric, but you kind of cut it into small powder, and then you know that gives you a lot of flavor. Similarly, in Ayurveda, in medicines, we used to use ashes, which are basically nanoparticles, right? So the idea then is there was never a systematic study in the past to understand exactly what goes at the nanoscale. So we are slowly now beginning to understand some of the important aspects of the nanotechnology. So today I'm going to share with you, not the whole thing just to be focused. I'll talk a little bit about the magnetism at nanoscale. Right? So although I'll give you a brief introduction to the nanotechnology, talk several examples of magnetic nanomaterials, we'll look at the applications. In the end, we'll also talk a little bit about the COVID and how the nanotechnology is helping in terms of fighting the pandemic. So that is the plan for my lecture. So In the outline, so I'll discuss about what is nanotechnology and the application of nanomagnetic materials. I'll give an overview and some selected examples of nanoscale materials. In our laboratory, we have done so many materials at nanoscale and examined their properties. So I'm not going to go over all the work, but I'll just give you selected examples of that. And then finally, I'll give you some conclusions. So that is the plan. So what is nanotechnology and why it is now? All right, so here is the important aspect. When you take a material and then bring the size of the material into the nano regime. So at this time, I think it is important that I need to define exactly what do I mean by nano. So any material, at least in one dimension, if it is less than 100 nanometers, so this is very important, at least in one dimension, if it is less than 100 nanometers, then I can call that safely a nanoscale material. And when you bring the materials to this scale, they have properties completely unpredictable. So I'll tell you why it is so unpredictable in a minute. So if you look at this picture here, on the left-hand side, I have a bulk material, and on the right-hand side, I have a nanomaterial. So if you look at the left-hand side picture, you have a lot of atoms or species inside the boundary, and on the surface you have very few atoms. So if you take the ratio of number of atoms to the surface to the bulk, it's very small on the left-hand side, but when you go to the right-hand side, that ratio increases tremendously. That means number of atoms in the surface to number of atoms in the bulk increase. So what does that do to the material is the next question. So making a material at the nanoscale can change several properties, and I'm just giving you a few properties. Now, if you look at this slide, some of you may be thinking, oh, okay, melting temperature changes, okay, magnetization changes, supercapacitive properties change, structure changes, chemical reactivity. But if you are really paying attention to this, I'm going against the classical theory of thermodynamics. We were told in all our chemistry classes that the melting point of a material is unique to that material, right? No two compounds can have the same melting point. But then here, when I go to the nanoscale, I'm violating that principle. That is, you can change the melting point of the material by changing the size of the material, not the chemical composition, not the chemical identity, just the size. So if you physically limit the size to nano dimensions, you are able to create new melting temperatures. For example, gold, in a bulk form, it might melt around 900 degrees Celsius, but if you make it sufficiently nano, you can melt gold at 150 degrees Celsius. So the melting point of gold then depends on the size of the gold particles. What is this telling us? All right, let's keep that for a minute. Let's talk about the next property, magnetization. We were told the magnetization of a material is a thermodynamic property, and hence you cannot play with this. Magnetization should be a constant property. It should not depend on any other factor. But then when you take the materials at nanoscale, suddenly we see a dramatic change in the magnetization properties, completely in contradiction to the laws of thermodynamics. Structure, chemical reactivity, among other things. So what is this telling us? This tells us that materials at nanoscale do not obey classical laws of thermodynamics. Remember, we were told thermodynamics, there are laws of thermodynamics, you cannot break them, but in nanoscale we do. So which implies that you cannot predict the properties of materials at nanoscale based on the classical thermodynamic principles. This is the most important message. So what controls the properties then? Maybe quantum mechanics? Maybe something else is controlling the properties there? So today, even after research for 25, 30 years in the areas of nanotechnology, we don't have a model to tell us exactly how a material behaves at a nanoscale. The only way we will know that is by doing it, not by looking at the theory. So I want you to keep that in mind as we go through this presentation. So this is the most important, one of the most important takeaways of the talk, is that thermodynamics doesn't apply to materials at nanoscale. So nanomagnetism. Why are people interested in nanomagnetism? I just want to make sure that you're all able to see the slides, right?
Yes.
Yes, sir.
Do you
Yes,
see the
sir.
slide nanomagnetism? Okay,
Yes,
great.
sir.
Okay. All right. All right, here are the things. Nanomagnetism has picked up a lot of interest in the last maybe 10, 15 years because of myriad of applications these materials have in different emerging technologies. These are not the technologies for today. These are the technologies for the next 5 years or 10 years down the line. For example, there is a great need to make ultra-strong permanent magnets. The magnets that we have today are not enough. The hysteresis curves are S-shaped. We want to go from S-shaped to square-shaped hysteresis curves. And we are also looking for ultra-high density media. And there is a lot of work going on in spin polarized materials, room temperature magnetic semiconductors. These are also known as dilute magnetic semiconductors. Sometimes this is also called a spintronics area. And instant boot up computers. You know, today when you turn off the computer and turn it on, it takes at least a few minutes, depending on the model of your computer. Sometimes it might take even 5 minutes. So the question is, can we have a computer that you turn it on, just like a light bulb, it should turn it off? And spin-based qubits, computer-based test tubes. I don't know if you know this or not. Recently, there is a lot of excitement in terms of making computers from DNA. The human DNA can be used in a test tube. By using the strands and the orientation of the DNA strands, we should be able to store and process the information. This is amazing. Similarly, nano biomagnetic sensors. This is also picking up a lot of area. This area is already there in animals. It's just that we are only now slowly understanding how certain animals use the magnetic fields to do the navigations. Finally, there is also the hope that one day, by using just 25 atoms, we will be able to create a computer that can store hundreds of terabytes of information and process the information at speeds that are at least 1,000 times better than what we know today. Keep in mind, just 25 atoms. All right. The reason for that is atoms have electrons. Electrons have two aspects. They have a charge and they have a spin. The charge of an electron can be harvested and take the role of a silicon in the processor. The spin of an electron, by virtue of the spin, it creates a magnetic field, so you can use the storing. So by configuring 25 atoms in a careful matrix, we should be able to both store as well as process the information simultaneously. In other words, the future computers will not have a separate processor and a separate hard drive. The processor and hard drive will be integrated, and all that into a space of about 25 atoms, less than a nanometer. So that is where the technology is moving, and there's a lot of interest it is generating. So let's look at the general idea about what exactly is nano. So I'm just giving you here biological length scales. On the rightmost, I have the diameter of a human hair. It's about 120 to 130 microns. A micron is 10 to the negative sixth of a meter. So starting from there, if you move to the left, you slowly start getting particles that we all know. We all know what a pollen is, but maybe if some of us know that pollens have about 15 to 20 micron size. Then when you go into these cells, they are between 10 microns to 100 microns. And then we go into red blood cells, which are between 1 to 10 microns. And once you get into bacteria, which we all know, they are of the size of a micron. Then when you get into the nanoscale, which is 10 to 100 nanometers, you get into species such as proteins and the viruses. The COVID-19 virus that we are talking about is approximately 120 nanometers. We'll get into that also later in the later part of the presentation. So as you cut down the scale in aspirin molecule, it is subnanoscopic material, less than, it's about 10 to 15 angstroms. And buckyballs, they have about 1 nanometer. The DNAs are anywhere between 3 to 5 nanometer scale. So it kind of gives you an idea about how small this matter is relative to the diameter of a human hair. So these are extremely tiny materials that we're dealing with here. All right, magnetism and medicine. So there is a lot of interest today in applying magnetic materials in the healthcare industry. Because you have pharmaceutical sciences in your department, it may be important to realize that this magnetism plays a very important role in the development of therapeutics as well as drug delivery materials. We'll get into that too in a minute. We all know that iron, which is very important for living things, and many animals use magnetic fields to navigate. This is really curious. If you look at the whales from the Australian Ocean, they travel about 3,000 miles, go to a place in the California area, stay there for about 2 months, and get back to Australian things without using a GPS. They don't have a cell phone, they have nothing. How do these animals do? How do they remember where they come from? What exactly guides them? What is the navigational tools these animals use? Apparently, it so happens that these animals are able to use their biological complexes of iron and orient that to the Earth's magnetic field and use that magnetic information as an information for going from place A to B and come back to the place A without losing their directions. So it's kind of amazing. We are only learning now. Hopefully one day, we will be able to master this and we can throw these phones out and use our own iron cis complexes to initiate the navigation. Synthesis of hemoglobin is very important because hemoglobin is an important chemical that transports oxygen to various cells, and the role of iron in neurodegenerative diseases. There are two elements that are extremely important for mental health. One is iron. The other one, what Dr. Reddy has talked about, the lithium. Dr. Reddy talked about lithium-ion batteries, but lithium ions play a very important role in the manic psychiatric disorders of humans. So it's very important to keep that in mind too. So the inorganic materials and the ions play a very important role here. And for the medical applications, removal of iron splinters and sharpeners and holding the prosthetics, magnets are used to hold the prosthetics. And they're also used for guiding instruments through the body. So they can use the magnetic fields, external magnetic fields, and guide them to proper places in the human body. All right. So MRI, we all know about this. Magnetic resonance imaging is a very important tool in the diagnosis. The MRI scans are done routinely in the hospitals to find out the damage to the cells and tissues. All right. So biomedical applications is magnetic imaging, magnetic heating. I don't know if you know this or not, but if you take a magnetic material, small size magnetic material, such as a nanomagnetic material, and put it in a tumor site and apply external alternate magnetic field, that alternate magnetic field creates what we call friction, like Brownian motion and all that stuff. Hysteresis loss comes in the form of heat and increases the local temperature of the tumors just by 5 degrees Celsius, which is enough to kill it. So once you achieve 40 to 42 degrees Celsius near the tumor site, local heating I'm talking about, that is enough to kill the tumor. So nanomagnetic particles are getting a lot of importance in terms of creating this kind of hyperthermia treatments. And targeted drug delivery. Can I deliver the drugs directly to a particular spot in the human body rather than circulate the drug through all the entire human body? So that is another area that is picking up interest. So this way we can minimize the damage to healthy cells and cure only the cells that need repairs. And this, of course, there's a detection, purification, isolation, manipulation of the cells. So there is a lot of work that is going on in the area of nanoparticles, especially nanoparticles that have useful magnetic properties. So we'll talk a little bit about the selected examples of nanomagnetic materials that we have worked over the past 5-6 years. I'm not going to give you all the samples, but I'll just give you some representative examples of how these particles look and what are their magnetic properties. Remember, magnetic property is supposed to be a thermodynamic property, right? So we're not supposed to touch the properties. No, when I say touch the properties, if the Curie temperature of a material is 150 degrees, that should be 150 degrees for that material, no matter what the other conditions are. But then when you make it nano, suddenly that temperature may not be 135. In other words, the thermodynamic principles don't apply here. So let's look at the first example. Here I have a very simple compound, nickel oxalate dihydrate, NiC2O4, 2H2O. We were able to make the particles, the diameter of 250 nanometers and length is about 2.5 microns. And this material, when we looked at the magnetic property as a function of temperature, starting at 300 degrees Celsius, if you start cooling down, at about 45 Kelvin, we start seeing a dip in the magnetization. What this decrease tells you is the material is getting ordered antiferromagnetically below 45. But then you look at the bulk material, that's not supposed to happen at 45, but it should be happening at 50K. So in other words, what happened is, when I reduced the size of this material, I was able to push the antiferromagnetic ordering temperature, in a world of physics, we call it the Néel temperature, from 50K to 45K. Again, I'm defying the laws of thermodynamics here. All right, let's look at the other material. What we did was we changed the nickel to cobalt here, cobalt oxalate dihydrate in the nanoscale. Suddenly what we see is the Néel temperature in the bulk is supposed to be 18 Kelvin, but in the nanoforms, suddenly that increased to 54. Compare this to the previous example. In the nickel example, the Néel temperature reduced from 50 to 45, but in the cobalt, it increased from 18 to 54 Kelvin. See how much of manipulation we're able to do just by reducing the size of this particle. Again, I reiterate this. This is not acceptable to the classical thermodynamics people because it does not explain. Thermodynamics cannot explain this. Moving on, simple materials like copper oxide, which we made from heating copper oxalate at very low temperatures, making nano copper oxides. Depending on the size, we were able to make two different sizes, 25 nanometers and 80 nanometers, and we were able to shift the Néel temperatures. You see, bulk is 230 Kelvin. When the particle size is 80 nanometers, that Curie temperature is 220K, and when it is 25, it gone down to 80 Kelvin. So we are able to manipulate the onset of the ferromagnetic transition temperature just by playing with the size of the particles. This is amazing. This is totally unexpected. Similarly, cobalt-3 oxide, which is a spinel structure here, we were able to again play the magnetization here. In the bulk, it is supposed to be 40K, but we were able to bring it down to 35K. And also, we were able to play with the ferromagnetic ordering temperature of the cobalt by reducing the size to 20 to 25 nanometers. So in the bulk, cobalt is one of the strongest ferromagnets known to humans with a transition temperature of about 1400 Kelvin. But when you bring it down to 25 to 25 nanometers, you not only get rid of the ferromagnetic ordering, but you get into what we call a super paramagnetic order, and the magnetization behaves very differently. Similarly, we also looked at iron-nickel alloy systems. Again, these are all the X-ray characterization. The reason why we show this is, as Dr. Reddy has said, we just have to make sure that our compounds are pure and there is no other impurity in this material. So this characterization is very important before you start studying the properties. So that's the reason why we show this diffraction patterns. Depending on the composition of iron to nickel, it could be the body-centered cubic system or a face-centered cubic system. And then we were able to look at the TEM pictures of this and look at the HRTEM graphs. And we looked at the lattice spacing and lattice imaging. In all cases, we see the compounds are approximately 18 to 25 nanometers in size, depending on the ratio of iron to nickel. So these are all the additional pictures just to show you that there is a lot of uniformity here. So the next thing we did was iron cobalt. So iron cobalt also behaves very differently. In the field of metallurgy, when you take an iron and a cobalt, there are only certain phases that are possible. These are called the Hume-Rothery ratios. But when you go into the nanoscale, again, the Hume-Rothery ratios don't work. You can pretty much prepare nano alloys of iron to cobalt with any ratio that you wish. That's what this graph shows you here. And we were also able to see nice TEM pictures. The average size of the particles is extremely tiny. You can see 5 nanometers. That is a very, very small particle size. And we also looked at the EDS studies, energy dispersive spectroscopy, and we were able to figure out the compositions, that is the ratio of iron to cobalt in these things. The important thing here is the saturation magnetization values do change depending on the ratio of iron to cobalt. So we were able to create materials with varied saturation magnetization moments. So this is a very important development in that area. Similarly, we were also able to make copper to nickel alloy structures. These are extremely 3 different compositions we looked at, 123, 121, and 321. In all cases, we were able to both look at the TEM and X-ray line broadening to find out the particle sizes. And here are the particles. They're extremely tiny. As you can see, they're about 7 nanometers. And if you look at the magnetization values, if you have 1, 2, 3, the saturation magnetization is about 6,000. And when you bring down to 3 to 1, the saturation magnetization is only 300. So you can play with the saturation magnetization values just by changing the ratio of copper to nickel. Similarly, iron to nickel ratios, we were able to make different type of particles. Most of these particles are prepared by what we call reverse micelle technique. That's not a very efficient technique, but a technique that gives you more uniform sized particles. So that is why we did this. And again, we can see iron nickel giving FCC and BCC structures. These are all different compositions, average particle sizes, saturation magnetization. This is very important for technology. They want to know what is the maximum saturation magnetization the material has. In addition to pure nanostructures, we were also able to make what we call core shell structures. So for example, we can take a core, one material, and a shell, a different material, and be able to create nanostructures, which are amazing. So we're able to do that for copper and cobalt by manipulating, as you can see in the right-hand side bottom, you have definitely a core inside and a shell. So the core and shell have very different magnetic properties and structural properties, and that also modifies the overall behavior of the particles. Similarly, we were also able to make not only the metals, but the oxides as well, the core shell nanostructure. This is very important for computational applications. So here is an example of CO3O4, SiO2 core shell structures, and the particles are definitely less than 100 nanometers. These are extremely nano-sized particles, and we were able to create very wonderful architectures that are useful for computational applications. So when we looked at the magnetization studies, again, there is a reduction in the magnetization whenever you put silicon because SiO2 is non-magnetic. So we kind of modeled the magnetism in the nanomaterials by using what we call a superparamagnetic moment. So here is a nanoparticle that contains, there's hundreds of atoms within. So each atom has its own spin oriented along this direction. That's the ferromagnetic orientation. So if you look at the entire particle, it looks like a super spin of this. So this particle, instead of looking at it as different spins, we have a combined spin, what we call a super spin of this particle. So this is the one that we are measuring, trying to saturate at very high magnetic fields. So when we look at the particle sizes, the critical magnetic field and the coercivity also changes in a very peculiar way. So in the low nanometric regime, the coercivity increases as when you increase the size, but when you increase the size above 1 micron, suddenly what happens is the coercivity decreases. So what this tells you is the coercivity of the particles can also be modeled by changing the particle sizes. So coming back to the biomedical applications of all these materials that we have been talking about, so you can take these magnetic materials and use them for magnetic imaging, heating, targeted delivery, and manipulation. So looking at hyperthermia, we know that cancer cells growth is stopped or completely inhibited when the temperature of the local tumors are in the range of 42 to 46 degrees Celsius. So magnetic materials, when you inject them into the tumor and apply external magnetic fields, the external magnetic field, especially if it is an alternating magnetic field, changes the direction of the spin during the course. It has hysteresis loss, Brownian motion, and eddy currents. And all these three manifest themselves in the form of heat locally in the tumor, and that is enough to kill the tumor. The importance of nanoparticles is because they provide uniform heating compared to any other means of supplying heat. They are non-invasive delivery, and once you put the nanoparticles on the tumor surface, you can leave them there for multiple treatments. So you inject them only once, and you can use these nanoparticles multiple times, so you can slowly kill the tumor over a period of 2 to 3 weeks without injecting new particles. There are human clinical trials that are in progress right now. The other thing is magnetically targeted drug delivery. This is a very important area that is coming up. The reason for that is, as you all know, old people and small kids have trouble taking the medication on time. Old people, they forget taking the medication sometimes. Sometimes they take the medication and they're in doubt, oh, did I take the medication or not? And for the safe side, they take another one. Sometimes there's a drug overdosage that kind of kills people. So there is a lot of research that's going on in using these magnetic particles, especially nanomagnetic particles, and tag them with the drug molecules and inject them, and so that the drug is released slowly over a period of, let's say, for about 2 to 3 weeks. So the patients take the drug only once every 3 weeks rather than taking 3 times every single day. So that is the type of direction that we are going. So patients don't take the drugs correctly, and many drugs are highly toxic even in small amounts. That's the reason why if you take the drug 2 times, that sometimes give you, as you all know, the deleterious toxic effects there. And the other problem is systematic biodistribution is another big problem, especially with cancer drugs, because they're not hydrophilic. And pharmacokinetic variability is a big problem. So here is the method that people are looking at. Let's look at a mice here with a tumor right here. So what you can do is you can take a syringe, inject magnetic nanoparticles such as the iron nickel or iron cobalt, depending on the saturation magnetization. You can calibrate and inject them and bring an external magnet. So what the external magnet does is it takes all these nanoparticles and accumulates them in the tumor area. In other words, these magnetic particles go to the tumor, not everywhere in the human body. So this is a very important distinction of using magnetic nanoparticles in the case of treatments. All right, so if you look at the cancer drugs, we all know, I think yesterday, Subhash talked about cancer agents, and Professor Reddy Mayreddy also talked a lot about the biology of the cancer drugs. One of the biggest problems with anti-cancer drugs is they have very high non-specific toxicities. And we know that effect. When you see a patient who is going chemotherapy or radiation therapy, when you know this, they go through a lot of pain. That's because they have high non-specific toxicities. And another problem is anti-cancer drugs are hydrophobic. What this means is, instead of giving a small dosage, for the drug to be effective, you need to pump in at least 10 times more. So how can you change this? So if you can make this a little bit more hydrophilic, you should be able to improve the bioavailability of these drugs. So that is another area. And another big problem that is happening is, over a period of time, some of the cancer cells are getting resistant to the drugs. So they're developing what we call drug resistance. And so what that is doing is, now instead of using one drug, you need to use a cocktail, 2 or 3 drugs together. So the problem again is the drug loading capacity and release profile. You don't want the drug to be released pretty quickly or very slowly too. So you need to be able to control the release profile of the drugs, and aqueous dispersion stability and phagocyte stability is a lot of stuff that get into the picture here. Circulation time and biocompatibility of these small molecules, and the magnetic properties and targeting and the retention. So these are all the issues in terms of using magnetic nanoparticles for the drug delivery. So I'll give you one example of this. We all know that iron oxides are biocompatible and they're also magnetic. So here is a sample iron oxide nanoparticle on the right-hand side. So what we do is, to load the drug molecules into these magnetic nanoparticles, we kind of attach oleic acid, which has a long hydrophobic tail, to the iron oxide and create the nanostructures like this. And once you do this, the oleic acid tail is hydrophobic. So the problem is iron oxide will not get into the human blood. So what do we do here? We kind of take a pluronic, a very composite material that has a hydrophobic middle and the hydrophilic tails on both sides. And these are phagocyte resistant. That means they will not be attacked by the human cells. Now, if I take this and attach it to here, as you can see, the hydrophobic tail here now attaches to the oleic acid, and now the surface becomes extremely hydrophilic because that is how I made the nanostructure. Now, once I take this one, hydrophilic surface, I can take the drugs and attach them chemically or ionically. And of course, there are some issues, but we are slowly overcoming this, and this is becoming a very attractive technology. So here is how you do this. So here are the nanoparticles, and you add the drug molecules here. The drug molecules are shown as red dots here. And once you evaporate the solvent, what happens is that now the drug attaches it to the nanoparticle. So this nanoparticle now can be injected to humans, and this will slowly release the drug very nicely. So I'll show you in the next plot very quickly the doxorubicin, which is the gold standard for cancer treatment. Once you put that one on the iron oxide nanoparticles, and when you looked at the release, as you can see, at least for 15 days, for almost 2 weeks, the release profile is very stable. So you don't have to inject doxorubicin every day. Instead, you can use these magnetic nanoparticles to deliver the drug in a slow profile over a period of 10 to 15 days. So they are released very slowly, continuously, and in a non-toxic fashion. So this is an area that is picking up a lot of interest. So the way we can also direct these particles to a particular side of the human body by using an external magnets, that is because of the very strong magnetic moment of the iron particles here. So the other one, I'm going to quickly, because I'm running out of time here. I have 3-4 minutes. I just want to quickly touch base with the COVID-19. The reason why I bring COVID is because COVID is also a nanoparticle with a size of about 60 to 140 nanometers. That is the size. It has, of course, you all know the spike proteins and membrane proteins, cell proteins, and all that stuff. So this is the overall topography of a virus here. The spike length is again in the nanometric scale, 9 to 12 nanometers. So there is a lot of work now going on in terms of designing nanobodies. Please understand, I'm not talking about antibodies here. I'm talking about nanobodies that can go and attach to the spike proteins. If you can deactivate the spike protein, the virus gets entirely deactivated, because the way the virus attacks the human cells is through the ACE2 receptors, using the spike proteins. If you disable or completely deactivate the spike proteins by using nanobodies, you should be able to control the infection. And I was very happy to see just 3 days ago a nice paper coming out in terms of designing the new nanobodies for treating this pandemic virus. So this is a scanning electron micrograph of the coronavirus. It's about 100 nanometer scale. As you can see, these things very nicely, sub-nanometer scales, about less than 100 nanometers. Remember, I told you all viruses are not of the same size. And you also have to keep in mind, coronavirus, there are 6 different variations of the coronavirus. The COVID-19 is a different variation. But in general, in the atmosphere, we have 6 or 7 different types of corona particles, coronaviruses. So here are some of the physical properties of this. The radius is about 30 to 70 nanometers. So you can calculate the volume. The weight of a single virus particle is about 10 to the negative 18, 68 attograms. It's an extremely small one we're talking about here. So as you all know, the breath has large droplets, small droplets, aerosols. So these are all micron-sized particles, but within the micron-sized particles, you have the nano-sized viruses. So this is where the interest is. So these are all some of the studies our friend we have done together here. I don't want to get into that, but there is a lot of interest in terms of detecting the viruses using simple infrared and Raman spectroscopic methods. As you all know, infrared spectra is very quick to do. It takes less than a minute. So we're trying to develop some substrates that can hold on to this spike protein of the COVID and be able to look at the IR stretching differences and be able to detect within about, let's say, 5 minutes, rather than taking 3 to 4 days, what it's taking now for the PCR testing. So the current research is a lot of inorganic chemistry in managing the virus is being looked into. Slowly, it is getting to a point that the deficiency of certain elements in the human blood may be a reason for why some people get more sick compared to other people. So there is a theory that says copper, for example, is a very important, although it's an extremely tiny amount of copper in the human body, but any small fluctuations can have dramatic effects in terms of how the COVID is going to attack the human body. So this is something that people are looking into, looking at the blood plasma to see how the copper content of the human blood correlates with the severeness of the sickness. So there is a development of new vaccines, rethinking about our food habits and prophylactics that are cheaper and safer. So several elemental metals have been tested for the deactivation of the virus. Okay. Of all the elements that have been tested, apparently copper has a spectacular ability to deactivate the viruses in a short period of time compared to stainless steel. So if you look at your faucets or the fomites or the kitchen top surfaces, most of us have stainless steel surfaces. But stainless steel is known to keep the virus at least 3 to 4 days. And recent studies have shown that the virus can stay on the stainless steel surfaces as long as about 3 weeks. So that is a very dangerous development. So, but humans have seen for thousands of years that copper has a spectacular ability to deactivate the viruses, not only the coronavirus, in general, any virus. So copper deactivates viruses much faster than steel, plastic, or clothes. Enrichment of plasma copper levels is hypothesized for improving the immunity. So people are looking at, suppose if they can improve, put a little bit of more copper in the human blood, would that act like a prophylactic? It's a preventive medicine for getting the virus. So here is a study that showed in air, the virus can stay for about 3 hours, and the copper is about 4 hours. If it is a cardboard, it can stay for 24 hours. Stainless steel, 2 to 3 days, sometimes can be up to weeks. And the plastic, up to 3 days. So most of the surfaces that we touch today are mostly cardboard, stainless steel, or plastic. So instead, there is a push now in the industry to change all these surfaces to copper. So for example, the door handles in Australia now are being changed from stainless steel to copper, as you can see here. And that is happening in America too. I'm sure you will see that happening in India too very soon. All your fomites, the touching surfaces will be coated with nano-sized copper particles. So these are all the machines, nanospray machines that are being developed in Australia for commercial use. So you can take any of your touch surfaces and put them in the machine, make a coating of nano copper and take it out. All right, so finally, I want to leave the talk with a simple caution for people working on the nanomaterials. Although nanomaterials are fancy to work with, but there are some dangers too. So here is some of the things that I always ask people. If there is a new technology that is going to change the world, but it will kill 50,000 people, would you be in favor of it? Many people think, no, we can't afford to lose 50,000 people because of the technological advantages. But what we sometimes forget is we still live with that kind of world. For example, if you look at an automobile, it kills more than 50,000 people worldwide, but we still cannot get rid of this technology. So what do we do instead? We practice safety. All right. So there are concerns with the nanotechnologies, especially nanoparticles. Even if you wear a mask, it's not going to help you because these particles are very tiny. They can go into the lungs and cause a lot of damage to the lung tissues. And there have been some studies to show that the carbon buckyballs can cause extensive damage to the brain cells of the bars. So these are all some of the important aspects. So when you are working with nano, please make sure that you follow all the protocols as careful as possible. This is not a funny thing. Any dust or airborne particles, when they go into the human body, it's very difficult to get them out. So if you are practicing, if you are trying to do any nanotechnology, please be very careful. Sometimes they find that the curvature of the nanoparticles also has an important effect on the health. So these are all the things. So basically, I would like to conclude this talk within the time that was given to me. Nanotechnology offers great promise for the future, especially in the medical applications. There are many potentially positive implications for nanotechnology in medicine, which I think I have shown you. And it's critical to understand how nanomaterials behave differently than bulk counterparts. We don't have any models right now. There is nothing that will tell me that if you reduce the particle size to 15 nanometers, what will be the Curie temperature or the Néel temperature? We cannot predict. So unfortunately, even today, we have to do an experiment to see what effect it has on the physical properties. So we need to slowly move into modeling these materials. So we have to stay tuned for the future. I think it's going to be very exciting with all the developments of the nanoparticles. All right, and I thank you this time. And sorry, I think I have gone 2 minutes over the time. And I appreciate you all listening to this presentation.
Thank you, sir. Thank you very much for a valuable and fantastic session, sir. It's also well explained about the challenges and nanomagnetism. Also, how to reduce the areas and personal computers with the integration of hard disks as well as processors using nanomaterials. It's a very excellent idea, sir. It's very innovative also. And also very much useful in the explanation of the magnetism and medicine. Also, how to use the natural GPS in the birds from one country to other country. It's a excellent, sir. It's a nature GPS. That is also included in the nanomagnetism. So well explained, sir. Thank you very much. And also selected examples for the nanomagnetic materials like copper, nickel, iron, nickel alloys in the nanoparticles. And also it's a very useful and innovative that is going to be the magnetic targeting, sir. That is in especially in the anti-cancer drugs. That is also very much useful. That is also issues in the anti-cancer nano drugs also. So also finally, it's very useful to detect the virus like the pandemic situation, the COVID-19, the coronavirus. How to detect by using the nanomaterials is also well explained, sir. Thank you very much, sir.
Dr. Shari, I also want to say hello to Professor Mandava Basaveswara.
Yes, sir.
Thank you. Very nice to see you, sir. How are you?
Thank you, Shankaracharya sir, for giving an overall brief about today's lecture by Ramanujacharya sir. And thank you once again, sir, on behalf of this international webinar.
Thank you, madam. Thank you, sir. Thank you, sir.
We came to the next part of our program. I request today's special guest for this event, Professor M. Venkata Basaveshwar Rao, sir, Honorary Secretary, AP Academy of Sciences, Amaravati. Now, I request Mr. Amarinda, faculty from Chemistry and Pharmaceutical Sciences, please introduce today's special guest. Amarinda, over to Amarinda.
Hello, am I audible, ma'am?
Yeah, please
Hello.
raise your voice.
Yeah, hello, am I audible, madam?
Yes, you can proceed.
Yeah, good evening to one and all. It's my great pleasure to introduce today's special guest, Professor M. Venkata Basaveshwar Rao, sir, who is an honorary secretary for Academy of Science, AP Amaravati. Sir, Professor M. Venkata Basaveshwar Rao, sir, did his MSc from organic chemistry from Andhra University and completed MTech in computer science in Geetham University. So also did PhD from Northeastern Hill University, Shillong. He has also postdoc experience from National Institute of Immunology, New Delhi, and also from National Tsinghua University, Taiwan, Malaysia, Singapore. He joined in teaching as a assistant professor in Geetham University from 1997 to 2004, and served as a associate professor in the same Geetham University from 2004 to 2008. Later, he moved to Acharya Nagarjuna University to serve as a professor from 2008 to 2009, and later he moved to Krishna University to serve as a professor, and he is still serving as a professor in Krishna University. Sir also holded several academic admin positions like dean, dean, no, head, dean, and director, and special officer, warden, chief warden, placement officer, licensing officer, coordinator, and the director for NSS. Sir also published 400 plus national and international journals. He participated and organized 1400 plus national and international seminars. Under his guidance, 24 students completed their PhD work, and 27 students completed their MPhil. Sir also published 4 books and 6 reviews. And he also a member for honorary secretary of Academy of Science, Amaravati, Andhra Pradesh. He also a member for EC member for Krishna University, and academic senate member, former academic senate member for Krishna University, and he also former member for Academic Council, IGNOU, New Delhi. Sir has received several awards from the government of Andhra Pradesh and various organizations. To move to the awards, Sir has received a state award in 2011, the award from Andhra Pradesh 2017, the Memorial Award 2019. Sir is also a member for Royal Society of Chemistry, London 2013. He is also a fellow of Andhra Pradesh Academy of Science. He is also a fellow member for Telangana Academy of Science. This is a very brief introduction to Professor Venkata Basveshwar Rao, sir. So, on behalf of Department of Chemistry and Pharmaceuticals, technology in science and technology, sir.
Thank you, Amarinder, for giving very nice introduction about today's special guest. So once again, I welcome today's special guest for the event.
Thank you, organizing team, for your kind introduction. Honorable Vice Chancellor Arvind Kumarji, Honorable Registrar M. Yadagiri Garu, and Chief Guest of this international webinar, Padma Shri J.D. Yadav, President of Indian Chemical Society and Indian Chair for American Chemical Society, Honorable experts and Professor Shivaraj, Dean Faculty of Science, Osmania University, Professor Upendra Reddy Garu, Principal, and Professor M. Vasanta and Organizing Secretary Prashanthi, experts, delegates, and participants, good evening, everybody. I'm really delighted and honored to be with you all on the occasion of this valedictory function of International Webinar on Frontiers in Science and Technology. Really, it is a well-planned, well-organized, and such a giant personalities like Ramanjacharya Garu, MV Reddy Garu, Mer Reddy Garu, VG Yadav, my friend Yanshuk Khan, Shengil Han, and other internationally renowned personalities delivered on various topics in frontiers. We all proud to be Indians as we claim that when entire world has no education, we have great Nalanda or Takshashila universities. Whatever scientific innovations, advancements realized today, they have roots from India. But when we see now, as we climb, every invention has roots from India, such as zero was invented by Indian, and then Ayurveda was the earliest school of medicine, and then father of surgery, Susruta, whatever we say. But when we see the gross innovative index, we are far behind to the advanced countries. I congratulate the organizing team for rightly selecting the topic which promotes our innovations, as we strongly believe that when there is a quality higher education, there will be good research. When there is a good research, there will be an innovation. When there are quality innovations, there will be an industrial development. So this kind of seminar will promote science and technology from India, particularly motivating youngsters. When I see the participants, most of the youngsters are there. So it will promote science, education and research, for which we are all striving for. So I congratulate the organizing team for successfully organizing this frontiers in science and technology, and we are all happy to be part of it. And an eminent lectures we heard from Mer Reddy Garu, my friend Subhash, and MV Reddy Garu, VG Yadav Garu, Yanshun Hu, and Sangil Hin, all Sangil Han, all are eminent personalities, and all the lectures are really wonderful. We must encourage such kind of seminars, and will be always happy to be part of it. And I wish the Mahatma Gandhi University, Nalgonda, under the dynamic leadership of Arvind Kumar Garu and Yadagiri Garu and Upendra Reddy Garu, they will do many more wonders like this. Thank you one and all for giving me this opportunity.
Thank you, sir, for accepting your honor on behalf of Department of Chemistry and Pharmaceutical Sciences. Thank you very much, sir. Now, I invite to give a brief about this event by our faculty, Sweta. Please, for a minute. Sweta, please unmute yourself.
A very good evening to one and all. It was my immense pleasure being a part of this conference. Since morning, we had a very good, fabulous lectures and everything with the great lectures and with the innovative scientific lectures. And today we are having a very legendary professors with us. I feel very happy, and I learned many things from the nano side and from lithium battery side and lycopene presentations. I feel very happy to be a part of this, and I welcome, and I have, it was my really a great considerations for having you all in this session, sir. Thank you so much for having you all in this conference. Thank you, ma'am, and thank you for organizing committee from MGU. Thank you, sir.
Thank you, Sweta. Can I expect any feedback from one or two participants for a minute? Please unmute yourself for a minute. Can any participant?
Hello.
Hello. Yeah, ma'am, please.
Good evening, ma'am.
Good evening.
Myself, Ranu Biswas, Assistant Professor, BCDA College of Pharmacy and Technology from Kolkata.
Yeah, ma'am, please.
So I'm one of the participants from yesterday onwards. I'm seeing this program. It is a very nice, informative session. And special thanks to the organizing team for organizing this kind of the international webinar in this situation. And I am privileged so that you allowed one of the participants as there. I am the facility to say something regarding this program. All the speakers who gave the speeches there was very nice and very informative, and that was very lively. And not only me, my so many students are also participant of this program. I think they are now joined through the YouTube link. So once again, thanks to especially Prashanthi ma'am, because she is very, very live to anchoring this program. Thank you, organizing team. Thank you, MGU, and thank you all other faculty members of this organization. And one thing, belated Happy Teachers Day to all of you. Thank you.
Thank you, ma'am. Thank you very much for your nice words and for your valuable participation for the 2 days, 3 sessions. Thank you, ma'am. Anyone?
Okay, thank you.
Can I expect anyone? One more person? Please unmute yourself.
Ma'am, am I audible?
Yes, sir. Is it? Joshi,
Yeah, myself Ajit Joshi from Gujarat.
Sure.
And first, congratulations to all organic committee members and department and as well as university. Really such a wonderful session and well planned. And whatever the speaker really very knowledgeable. I don't have the word I can say because of the last presentation also really such wonderful. Is specifically given to information all the pandemic. So really, this all program well organized, systematic. I given to congratulations to all the association which jointly with Mahatma, this your organizing institute. So I thank to all participants. Maybe they have learned a lot of things about this 2 days international webinar conference. So thanks to ma'am, and really thanks. When I sent to you mail and you immediately respond me and call me in the evening, sir, sorry, and I am ready to help you. So thank you once again, ma'am. Thank you.
Thank you, Joshi, sir. Thank you for giving very good feedback about this event. So now it's time to propose vote of thanks. On 5th and 6th, the Department of Chemistry and Pharmaceutical Sciences is jointly organized a 2-day international webinar in association with Indian Chemical Society and American Chemical Sciences India International Chemical Sciences Chapter. On behalf of our department, I thank our Honorable Vice Chancellor Sir Sri Arvind Kumar Garu and respected Registrar Sir Professor M. Yadagiri Garu and Principal Upendra Reddy Sir, and for giving us an opportunity to conduct this program. And special thanks to President, Indian Chemical Society and Chair ACS Padma Shri Awardee, Professor G.D. Yadav Garu, for giving his consent to conduct this program. And Sir has also promised they would like to open student chapters on behalf of Indian Chemical Society and American Chemical Society at our Mahatma Gandhi University. And my sincere thanks to all the honorable guests, special guest Professor Shivraj Sir, Dean Faculty of Science and UGC member New Delhi, and all the valuable speakers and guests of honor from 5th and 6th, Professor Mereddi Venkatram Reddy Garu, University of Minnesota, USA, Professor Jonal Geda Subhash Sir, Rowan University, Head of the Department, Professor Yoon Suk Hak, Inha University, South Korea, Professor Vikramaditya Sir, University of British Columbia, Canada, and Professor Sangilhan Sir, Changwon National University, South Korea, and Dr. M.V. Reddy Garu, Institute of Hydro, Canada, and Professor Ramanjachari Sir, Rowan University, USA. And also all my respected faculty members, research scholars, and all valuable participants for their valuable participation and support towards this entire program. And on behalf of this, once again, I thank all my participants, honorable guests, guests of honor, and valuable speakers. Hope Department of Chemistry and Pharmaceutical Sciences of Mahatma Gandhi University will conduct many more programs I welcome you all once again for our future webinars, and I also request all the guests, sir. Department will conduct many more programs, and I welcome you all once again. Thank you very much, sir. Now, I request technical team to play national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा विंध्य हिमाचल यमुना गंगा जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाए जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 जय
Jai Hind.
Jai Hind. Once again, thank you for your wonderful participation during this two-day international webinar. Thank you, sir. Thank you, Basveshwar, sir, for giving time during this pandemic. Thank you so much, sir. We are blessed with your presence. Thank you so much, sir. Thank you, MV Reddy, sir, and thank you, Chari, sir, for your valuable presence during this tough time.
Okay, thank you very much.
Thank you, sir. Thank you, sir. Chari, sir.
Thank you, Prashanthi.
Thank you so much, sir. You are the behind of this entire story, sir. Thank you very much. We are blessed, sir. We are blessed. Thank you, sir. Sir, I like to conclude this meeting, sir. Bye.
Sure. Thank you very
sir.
much.
I will be in touch.
Have a good night. Have a
Thank
great
you,
night.
sir. Thank you, sir. Once again, thank you for all the participants on behalf of Department of Chemistry and Pharmaceutical Sciences. Thank you, sir.